The next 9 Laplace transform integrals. So if you have integral Laplace transform integral, integrals involving the function small f, and you already know Laplace transform small f, it is capital F of s. The Laplace transform the integral of this function small f, when it's 0 to t, will be capital S upon s. If there are two integrals, it will become f s upon s. Right? It can be generalized to more integrals. So here you have integration 0 to t cos 2t. So you know the Laplace transform cos 2t. It is Laplace transform of cos 2t is s upon s square plus 2 square. And by the definition, that's the result that we just saw. Laplace transform cos u du, which is 0 to t. Laplace of this function is going to be this beautiful function s upon s square plus so divided by s. So I can write it like this, and on simplification, you see that you get 1 over s square plus. So very simple. It's only in this rule. Otherwise, you can solve it by definition. If you know the rules, it becomes simpler. Simply 1 over s plus 3, 1 s plus 3 is u plus 3. Okay, it's always inverse. The Laplace inverse of 1 over s plus 3 is e to the power minus 3t. And here we have what? What we have? This upon s, right? So you apply this formula here. Here you can see that I write Laplace inverse of capital Fs upon s will be equal to integration 0 to t fu du. Right? So from here, this. So if you see some function divided by s, then Laplace inverse of that is, you must know its Laplace inverse, which is f of t or small f of u. It is integrated with 0. So here you can see this one. It is 1 over s plus 3. What is Laplace inverse of this? It is e to the power minus 3t, and we are interested in finding Laplace inverse of 1 over s plus 3 upon s, right? So this is capital F upon s. So this is going to be an integration of fu du. So this is a small function f function over here. I calculate it as minus 3u du, and limits are from 0 to t. So the integral of this is e to the power minus 3u upon minus 3, and between 0 to t, get other limits. So at t, we get e to the power minus 3t, and at 0, this becomes 1. And upon there is minus 3. You can simplify minus e to the power minus 3t upon 3 is going to be final. Now we see the important function, unit step function, and it is defined as 0 on u of t is 0 when t is less than 0. So this value, this function, right? This is the axis, t is less than 0 here, and u is taking the value 0. When t is then equal to 0, so t is greater than or equal to 0 here, and for this the value of u is what? This is the function. It says a step. From here, the integers. So this is called unit step function. It is called heavy side function. In MATLAB, you want to solve the problems with this. The name is heavy side only. The count is like heavy side. Now it has another relation, or you can say the general form. It is called split or delayed unit step function. It is written as u of t minus a. So a is value on the t-axis. If t is less than a, then value of u is 0, and if t is more than a, then the value of u is 1. So this is 0 and this is 1. Right? This is a step function, which is called a delayed or phased step function. More general step function. So when a is 0, you get this. The piecewise discontinuous function, you can write any function like this. I mean, in terms of unit step function, and this is called a bump function. So it's very visible from the diagram that we can write b of b as u of provided that a is less than b and more than 0. We can write it as unit step of t minus a minus unit step function t minus b. This property is important, that Laplace transform unit step function. So we can calculate also simple calculations, and Laplace transform comes out to be 1s of t minus a, u of t minus a, the Laplace transform comes out to be the power minus a by s. Laplace transform function f of t into u of t minus a. Now f of t, any function, is getting multiplied by the unit step function. So by definition, either it is 0 or it is f of t. So when is it 0? When t is less than a, and this is equal to f of t when t is greater than a. Laplace by f of t to u of t minus a will be e to the power minus s a. Laplace of f of t plus is get to this result. So you can see the Laplace of small f of t plus a is as good as capital F of, I'll just say that you will replace your t with t plus a, and then take the Laplace of that particular function multiplied with e to the power minus a. That will give the Laplace of this dot function with the displaced unit step function. So we can solve it by definition only. This is second shift theorem. Involves the unit step function. Now here there is a product of a function of t minus a with the unit step function of t minus a. And then it is giving you e to the power minus a s to capital F of s. Capital F of s is what? It is e to the power minus a s to Laplace of f of t. Right? So here you can see L of f of t minus a and u of t minus. They are same. They are both are functions of t minus. In the previous result, you have seen the Laplace of a function of t multiplied with the u of t minus a. So here is the difference between the two. This is a function of t minus a. This is a function of t only, and this is equal to e to the power minus a s into Laplace of the function of t plus a. Function here will be modified by replacing your t with t plus a. So this is the result that you saw, and is used a lot because you have any functions which we multiply the unit step function in order to make them continuous, and then taking the Laplace transform is required. So we use this formula a lot. So find the Laplace transform is sin 2t. 2 pi t is between 2 pi 4 pi. First of all, we can write the function f t as in terms of unit step function, sine 2t into u of t minus 2 pi minus u is 4 pi. Right? So this is the same. This is a piecewise function. We involved the unit step function, and now this is a continuous function. So we can write the given function like this with the involvement of unit step. We won't find the Laplace of this, so I can write Laplace of f of t will be equal to Laplace of the whole function. I'm not writing again. So this whole thing comes here. So it can be written as Laplace of sine 2t into u of t minus 2 pi minus Laplace of sine 2t into u of t minus 4 pi. And we just see this result that Laplace of any function multiplied with unit step function is e to the power minus as. This comes from here. And Laplace of f of t plus. So we have to replace t with t plus and then find the Laplace transform. Let us do that here. So by applying the formula, we can write this as e minus 2 pi s Laplace of sine 2t. This t will be replaced with t plus 2 pi. Similarly here, this t will be replaced with t plus 4 pi. When we open this bracket, it's sine 2t plus 4 pi. Here sine 2t plus 8 pi. Sine is periodic. 2 pi, 4 pi, they don't bit of a 2 pi, 4 pi. Sine has a bit of pi, so it does not affect it. Sine 2t plus 4 pi is again sine 2t, and this is again sine 2t. We find the sine 2t, and this is present, so I can take it common. So it is e to the power minus 2 pi s minus e to the power minus 4 pi s to Laplace of that, and that is 2 upon s square plus 2 square. So that becomes the transform function. That becomes the final answer. We come to impulse function. In a large force acts for a short time, then the product of force and the time is called the impulse. We define impulse as delta t minus a as 1 over epsilon, where t is between a to a plus epsilon, very small value, and it is 0 otherwise. Mathematically, so we find the impulse function. You can see this point is a, and this point is a plus epsilon, and this axis is t axis. This height over here is 1 upon epsilon. This height is 1 upon epsilon, and there is a rectangle over here of this height. The length of the rectangle is epsilon, right? What is the area of this rectangle? Epsilon into 1 by epsilon, 1. So when epsilon is very, very small, when epsilon goes to 0, this rectangle becomes a single line, right? And the line will be of height infinity, but this area will be 1, right? 1 epsilon into 1 by epsilon will be 1. Area is 1. So from here we can conclude things like this. We can write delta t minus a as infinite when t is equal to a and 0 when t is not equal to a. So at a particular point a, the value is infinite, right? This impulse is infinite, and everywhere else it is 0. We also can get from the definition that if the area under this particular curve between 0 to infinity is 1, right? Area of this strip is 1. Then we see how there are more properties, very important properties of this impulse function. These properties are called shifting properties. So if you have a function, you multiply it with impulse function, it gives you f of 0, delta t, so it will give you f of 0. If you multiply the given function with delta of t minus a, and on integration with respect to t on the whole domain, you will get f of a as the output, right? So it shifts all the values of t and gives you just f of a. Between 0 to infinity, both the properties remain same in the half of the domain also. So here you can see e to the power minus 5t delta t minus 2. This is an impulse function by this property delta t minus a between 0 to infinity. This is f of a. So it should be equal to f of a. The function f of t here is e to the power minus 5t. So this is going to be e to the power minus 5 a. A here is 2. So minus 5 into 2 e to the power minus 10. This one, the delta of t minus pi by 4, function here is cos 2t, and in this t you will put pi by 4 as per this particular property. We get cos 2 into pi by 4, which is cos pi by 2, which is 0. So this is going to be 0. Okay, then now we come to another method to find the Laplace inverse, which is by convolution. So before we study the convolution theorem, there is you must know what is convolution of two functions. So if there are two functions f and t, you can write the convolution between them. Convolution is a technique to combine two functions to get another function. So this technique is that you take one function in terms of u, take the other function in as a function of t minus u, and integrate with respect to u between 0 to t. So ultimately u will get eliminated and we are going to get an answer in terms of t. So this is called convolution. Now in Laplace transform theory, there is this theorem called convolution theorem. It says that if there is a convolution, then Laplace transform of the convolution is going to be a product of the Laplace transform of the two functions separately. So you should know Laplace of f, you should know Laplace transform of g, you just multiply them, right? Just multiply them and you are going to have it equal to Laplace of the convolution of f and g. You must know that this is not a product, this is not a multiplication. From here we can write L inverse of fs into gs. So it is a function Laplace of f of t, small f of t. This is Laplace transform of small g of t. L inverse of their product is equal to the convolution of small f and g, which is integral 0 to t f of u g of t minus u du. So this is by definition, and this is the convolution theorem. So we can see here that we can write the function, this fraction, as s upon s square plus a square into 1 upon s square plus a square, right? Very much visible that this, we know L inverse of this thing, it is going to be cos a t, and this a is missing, so I can multiply with a and divide by a, so I can write this as this 1 by a, and this is now clearly the sine Laplace inverse of this is sine a t. Now we want to find Laplace inverse of this, so this is as good as the convolution of I can write it as L inverse of s over s square plus a square convolution with L inverse of a over s square plus a square, right? And this is 1 by a. This thing is cos a t convoluted with sine a t. Now what is this convolution? We just saw it is the integral in a particular way. We can write it as integral between 0 to t. We write one function, any one, you can write in terms of u. So I'm writing this cos a u, and the other one in terms of t minus u, sine a t minus u, and integrate with respect to u. Now we just have to integrate it. So you can see this is cos function, this is sine function. We have trigonometric identities which should be used, and then we just need to integrate it, and that is going to give us our answer. So let us solve. So we know this trigonometric identity over here, that 2 cos a sine b is sine a plus b minus sine a minus b, and we apply it over here. Your capital A here is au and capital B here is at minus u, at minus au, and we apply this identity, we get sine au plus at minus au, we get at, and sine of their difference is 2au minus at. Then we integrate. Integration of sine at with respect to u is going to be sine at into u, and integration of sine 2au minus at with respect to u is going to be cos 2au minus at upon 2a, right? Its derivative of this with respect to u is 2a, which comes here, and we apply the limit now. So this is 1 by 2a. At t we get t, so this limit is going in place of u, so t sine at minus at t you will have cos, so 2at minus at is going to be at upon 2a, minus at 0, this becomes 0, and minus minus plus at 0, you will have cos of minus at, which is cos at. upon 2a. So you can see this term is getting cancelled out, and we get finally 1 by 2a into t sine at. So by convolution we have calculated the Laplace inverse of this product of these two. You can solve it by other methods also. We can solve it by partial fraction as well, and there may be any other ways possible to calculate the Laplace inverse of this function. Similarly, you can see 1 over s square plus 1, 1 over s square plus 9, two different functions. We can solve it by using the convolution theorem. Now the last part of this particular topic is the Laplace transform of the derivatives. So if you know the Laplace of small f of t is capital F of s, then Laplace transform of f dash of t should be s into capital F of s minus f of at 0, small f at 0. Laplace transform of f double dash of t is s square into capital F of s minus s into f of 0 minus f dash 0. All these results have come from the definition of Laplace transform. Similarly, we can extend it to third derivative and higher order derivatives. So here we have this problem. It is an initial value problem, and dy by dt plus y is equal to cos 2t, and y at 0 is given to be 1. So we can quickly solve the problem. The first step will be to take the Laplace transform on both sides. So let it be 1. You take the Laplace transform on both sides. What is the Laplace transform of y dash, Laplace transform of y, and Laplace transform of cos 2t? So from this step, we can write this step. We are taking Laplace transform on both sides. Now, what is Laplace of y dash? If you know Laplace of y, so I am writing Laplace of y as capital Y at s. Then Laplace of y dash is s into ys minus y at 0. Right? This is by definition by these values, by these results. Laplace of f dash t is s into capital F of s minus f of 0. So here we have y dash, so s into capital Y of s minus y at 0. Now y at 0 is given to be 1. We are going to put the value here. Laplace of cos 2t is s upon s square plus 4. This value is 1, and ys is present in both terms. So as we discussed in the beginning, the very first lecture, that the aim of learning all these Laplace transforms is to solve the differential equations. The differential equations are, first of all, we take the Laplace transform and they get converted into algebraic equations. And once we get algebraic equations, they are easy to solve. When we solve them, we get the answers in terms of s. And then for those answers, for those solutions, we take the inverse Laplace transform to get back to the time domain. So we're going to do that thing here. So this is the process in which we took the Laplace transform. We got this expression, and now we are going to find capital Y from here. So you can see this s, and I can write this as s plus 1 into capital Y of s, and you have s over s square plus 4. This minus 1 can be written here as plus 1, and capital Y of s can be written as s plus s square plus 4 upon s square plus 4 into s plus 1. Right, so we have got this expression over here. This is s square plus 4, s plus 1, and we now have to find, so we have written this particular capital Y, and by taking its Laplace inverse, we can find the small y of t, the solution of this equation. So you can pause and see these calculations. Ys, which is this fraction, we are going to write it as a partial fraction. This is the linear factor s plus 1. We can write this fraction as a over s plus 1 plus another factor here is a quadratic factor. So for this we write bs plus c upon the quadratic factor s square plus 1. This is by the rules of partial fraction, and then we take the LCM on both sides. So on this is already fine. Here the LCM is going to be s plus 1 into s square plus 4, and the numerator changes a into s square plus 4 plus bs plus c into s plus 1. The denominators on both sides get cancelled and we get this expression. Now the aim is to calculate capital A, B and capital C. We compare the coefficients on both sides of s square, s power 1 and s power 0. So when you compare the coefficient of s square, you get 1 equal to a plus b. When you open this up, you get b into s square plus bs plus cs plus c. So there are 4 terms here. So from there we can see that a plus b is 1. Then a coefficient of s on both sides. So here the coefficient of s is 1. Here the coefficient of s is b plus c. The constant term here is 4, and here the constant is 4a plus c. Now if you look at these two equations, if you subtract them, you will get 0 and a minus c. And these two are in terms of a and c. We can solve them if you add both equations. Now this is simple system of linear equations. We want to solve them. So if you add these two, you can see you get 4 equal to 5. Your a is coming out to be 4 by 5. You know a, you can find b. So b is 1 minus a, right? So that becomes 1 by 5. And c is, so c can be written as 1 minus b. So 1 minus 1 by 5 is 4 by 5. Therefore, we can write the given expression, the partial fraction capital Y of s as a over s plus 1. So 4 by 5. Capital Y of s is 4 by 5 upon s plus 1 plus bs plus c 1 by 5 s plus 4 by 5 upon s square plus 4 s square plus 4. We are interested in finding the Laplace inverse of capital Y of s, which is as good as Laplace inverse of this. And you can see you can write 4 by 5 Laplace inverse of 1 over s plus 1 and 1 by 5 Laplace inverse of s upon s square plus 4, right? This over this, and plus 4 by 5. So, okay, 4 by 5 L inverse of 1 over s square plus 4. So this is 4 by 5, and L inverse of 1 over s plus 1 is e to the power minus 1t. 1 by 5. This is also, I mean, just by looking at it, you can see it is cos 2t. So 4 is 2 square, cos 2t, and here 2 is missing. So this 4 is 2 square. There should be a 2. So I can break down this 4 as, I can write it as 2 into 2. That is perfectly fine. We can do that. And now we can see L inverse of 2 by s square plus 4 can be written as sine 2t. Right? So that becomes the solution. L inverse of ys is small y of t. So we got the solution of the differential equation, and this is the solution. Right? So this way you can solve the differential equations, even the simultaneous equations. There must be one example. Okay, this is another problem where you have y double dash and y dash. So you can try it yourself. First step is you will take the Laplace transform on both sides. Then you have to use the formulas Laplace transform of yt you suppose, then Laplace of y dash and y double dash t you write on your own. Simplify, find capital Y of s, and then you take the Laplace inverse. For Laplace inverse, you can use whatever method you are comfortable with and you think which will be able to solve the problem, and that L inverse is going to be the solution of this equation. Now this is the system of simultaneous equations. So we have two equations in x and y, right? X and y both depend on t. So the same process, we take Laplace transform on both sides. We will get two equations in capital XS and capital YS. And you will solve those two equations for capital XS and capital YS. And then you will take the inverse transform, Laplace inverse of this, Laplace inverse of this, and you are ultimately going to get x of t and y of t. So I'll leave it for you. Thank you.